questions as well. We can look at some of those and I'll try to answer any questions. The last couple of things we're going to talk about, since this chapter is dealing with gases, is kinetic molecular theory of gases. Gases are actually quite interesting if you think about it. They really are. A gas particle, where does it get its energy from? How does it do the things that it does? For instance, if I took a ball, a tennis ball, imagine I took a tennis ball and dropped it right here. Boom. Now, when I drop it from here, number one, is it going to bounce all the way back up to here? Why not? Okay, a couple of things. One, gravity is kind of slowing it down. It speeds it up, but then it pulls back on as it's coming up. But, but you think about it, the amount of gravity that it's working with, it should get that much energy coming back. So really, we should get pretty much back to the same spot. However, the big deal is friction and also loss of energy when you collide. Take your hands and slap them together. What you feel is heat in both of your hands because you're imparting energy in both of your hands. So when that ball hits that table, it's actually imparting energy into the table, causing the molecules of the table to move faster because it put heat into the table, if you will, in the form of energy. So it lost its energy when it hit the table, and it doesn't have enough energy to go all the way back up. That's really why, because the loss of energy. That's called an elastic collision. That's what we're used to. When your car hits another car, you can feel that elastic transfer of energy. An inelastic collision, a completely elastic collision, I might have those words backwards, is when there is no energy change when two particles collide. A perfectly elastic collision. Am I using that word correct? I think I am. Yeah, they are elastic. That's right. Okay, so perfect elastic collision. No energy is transferred. So, in a perfectly elastic collision with a ball on Earth, if we dropped it, its energy should come straight back up, straight back up, straight back up, and that ball should never, ever, 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 ever stop bouncing. It should keep going all the time, all the time. That's how gas particles work. If you think about the particles of oxygen and nitrogen in your tire, outside in your automobile, your tire stays inflated all year round. You never have to put more air in it, take air out. It's always very inflated at 32 pounds per square inch. And if you think about what's going on to keep it inflated, is tiny little particles of oxygen are zipping around inside there, hitting the walls of the container of your tire. And the force at which it's continually hitting those tires is keeping that tire inflated. Now, there's not a lot of gas particles in there. If we were to say this is the inside of a tire, and basically, and I turned you guys into particles, that it would only take two of you in this room, two of you, to run around and, imagine this wall is like a balloon. It's like a balloon. It can deflate. And I need you to keep this completely filled up just like this, very, like a basketball or whatever this is, this room that we're in. So you have to run around as fast as you can. Punch the wall here, run back there, punch it there, punch it everywhere with enough force to keep that thing inflated. If you stop moving, the thing's going to, if you just take a break, oh, here comes the wall. It's all going to fly down. Are you with me? But gas particles are amazing. They never run out of energy. They're completely running around, zigzagging around, hitting all the areas, every spot, every couple of seconds, because they are hauling butt. We'll look at the speed of them in a minute. They're moving 500 meters a second. They're really going back and forth, hitting the walls of the container. But they never run out of energy. Because if they did, your tire would just go flat over time. So that's one thing about the kinetic molecular theory of gases. One, kind of know these. These are important. Gases consist of very small particles that are in constant random motion. Random. The only thing, when they hit a container wall, they don't lose any energy. They just change direction, or the momentum changes in the direction it's going. Gas particles are very small compared to the average distance that separates them. It's kind of important, because when you're measuring a volume of a gas, you're actually not measuring the volume of a gas. Did that make any sense whatsoever? Yes. Did it? You know how I like to talk. You'll measure what? The volume of the container. The empty air, if you will, the emptiness of a container. You're not measuring the volume of a gas. The volume of a gas is so tiny compared to the volume of the container that you're really, when you're measuring the volume of a balloon, the gas in the balloon, you're really measuring the volume of the emptiness in the balloon. The little gas particles are moving around, but there's almost no volume comparatively to a gas particle compared to the volume of the container. So even a while ago when I said 2 of you would be good particles, really you're too big to be a particle. I'd have to cut you about 50,000 times smaller, make you about this big. Maybe that would make more sense in the size of this room. 2 of those, this big, running around keeping this room completely inflated. Isn't that amazing? Say yes, that's amazing. Yes, that's amazing. Good. Now, collision 3. Collisions of gas particles with each other are completely elastic. They don't lose any energy. If they did, that'd be very bad. And the average kinetic energy of a gas particle is proportional to the temperature on the Kelvin scale. Kelvin scale. Meaning that, what is the Kelvin scale, by the way? Why is it important? Why are you laughing? Yes, sir. Seth is back.
It's temperature we can measure absolute zero, which is where nothing moves.
That's right. Very good. Kelvin, the Kelvin scale is not degree Kelvin. I never want to hear anybody say degree Kelvin. You can say degree Celsius or degree Fahrenheit. Never ever say degree Kelvin. It's not a degree. It's an absolute scale. Starts at 0 and goes up to whatever the hottest thing we know in the known universe is. Maybe a plasma star or something. But anyway, 0 Kelvin is absolute 0. Nothing can get colder than that ever. And at 0 Kelvin, just like Seth so eloquently said, 0 movement. I mean, nothing moves at 0 Kelvin because a little bit of movement causes friction, causes temperature increase. So at 0 Kelvin, molecules don't move at all. You put a little bit of heat into them on the Kelvin scale, boom, they're going from 0 to a lightning speed with probably a 500 millionth of a temperature increase in kelvins. I mean, they really go. Yes, sir?
That whole thing with things at absolute 0 not moving at all, does that only qualify for the random motion of particles, or like if you had something at 0 Kelvin and you dropped it, would that no longer be at 0 Kelvin?
You mean if it moved through space?
Yes.
Yeah, if it's touching anything and moving, that would give it. I understand what you're getting at. But if you keep it in an absolute vacuum, so there's nothing that it can do friction against, then you can move as fast as you want, because it wouldn't know it's moving.
Just no random motion.
Right. But no vibrations on the inside. The molecule itself could vibrate. But you know what? I do like that question. I like it. And it's going to keep me not thinking about it. Because I'm going to actually come up with a brand new law of the universe. Yeah. Right, and that goes back to my point. It's a relative thing. That's why I'm saying I like what he was just saying. You know, so I got to think about this on my head. But no, the question is, you're really talking about internal motion, internal vibration, movement of the molecule. Okay, so that's the kinetic molecular theory of gases. So speeds of gases, they're pretty fast, but we can calculate an average speed of them by using a very simple equation. Because what do you think the speed of gases are based on? I mean, obviously the temperature, but besides temperature, what else would make a molecule go faster than some other molecule? Say it. Nope. Temperature, mass, size, mass and size. The mass of it. Now, a heavier molecule with a little temperature is going to move, somewhat fast, but a very small molecule with the same amount of temperature, which is its energy, is going to move a lot faster. Remember, we kind of talked about that. If I had a bowling ball and a BB, the bowling ball I could barely move. Just if they're both moving at the same speed, the bowling ball is going to have more force when it hits a container wall than that BB would. If I want the BB to have the same effect on a wall of a container that moving bowling ball does, I'm going to have to speed that BB up a lot so it'll hit faster, and impart the same amount of energy. Does that make sense?
Yes.
So the size of a molecule. So here's your equation. It's really easy. The average speed. Now, the units might scare you because they don't really work out to like meters per second. But they do if you actually know what a joule is. If you know what a Newton is, which is a meter. It's a Newton meter. So if you know what these things are, then those units, 3 has no units, are kilojoules per mole Kelvin, joules, there's your joules, temperature, Kelvin, molar mass. The molar mass has units of kilograms per mole, not grams per mole. So if you use this equation, you can't use grams per mole, which is on the periodic table. You've got to convert to kilograms per mole. Because gases are so small, we've got to use none of them. So, all those units, when they cancel out, believe it or not, and you ought to prove it to yourself, because that'd be a fun exercise to do at home, that those units actually do convert to meters per second. So, this is how you can calculate the average root mean square speed of a molecule. And it's just based on its molar mass and a temperature. That's it. So be able to do that. Simple equation. Know it. Yes, ma'am.
Is the R always
No. The R can be 0.08206, depending on the units. Liters, atmosphere, mole, Kelvin. I'll give you the R's, but you know, I don't want you to memorize that. I don't even like making you memorize equations. Hell, I'll even put that equation up somewhere. You know, I'll put it up here if you need it. Diffusion and effusion. Here's the definition. A fusion is the passage of a gas through a small hole into evacuated space. Now, diffusion is when, if I open up a can of perfume right here, Cash is going to smell it before you guys in the back do, obviously, because it's diffusing through, you know, mixing with other gases. But effusion can be used to calculate lots of things. If you had a container that had a small hole in it, and if you put a mole of gas in it, no matter what that gas is, and let's say you had a pressure sensor inside that container. So you put a bowl of gas in, whatever the size of the container is, and it's got a little hole that you can open and close. And it's got a pressure, so you measure the pressure. You pull the hole out. Now, in here, this has got to be evacuated space. You pull a vacuum in it, so you do it in a type of glove box, if you will. But you got, there's no air in this room. And we sit here, we've got a mole of gas in it, we got a pressure. I pull the top off, and I hit a timer. And I go tick-tock, and I wait till the pressure goes to zero. Because eventually it will, because all the gas is going to come out here into evacuated space. Are you with me?
Yes.
So then I measure the time. Okay, I got a time for that. Well, then I can take, once I know that one, once I know what that was, I can use nitrogen, anything you want to use. I can take any gas you give me, any unknown gas, basically weigh it out so I know there's a mole in there. You got to put a mole of gas in there. So we can do that by using PV equals nRT. We can calculate the number of moles we would need. So we would put it in there so it's exactly 1 mole, based on its pressure, if you will. And then pull the lid off, let it go again, count it, get the time of that one. Those 2 times, I can easily calculate what the molar mass of that second gas was by using this equation. And I like the bottom one better, because time is easier than rate. But either one of those will work. But the bottom one, the time it took for component A, and we'll call component A the unknown. So if I don't know, if the unknown gas took 20 seconds, and the known gas, which is B, took 10 seconds, so I have those 2. The molar mass of A, I don't know what that is, that's what I want to calculate. And the molar mass of B, well, I chose that one, nitrogen or whatever. So I have 4 variables, 3 knowns and 1 unknown. So I can easily calculate the molar mass of the unknown by using that simple equation. Is that clear? Okay. I could do one, but I'm telling you, using those equations are easy. You should be able to do it. And I've got, like I said, that practice exam in a minute. Maybe I'll do that. Yes, sir, Sam.
It doesn't matter if it's grams or kilograms per mole now.
No. Because it sure does. Because it's still the ratio of those 2.
Yeah.
Okay. So anyway, those are the equations for that. Now, so deviation from ideal behavior. Let's think about this for a second. Let's see if we can think about the deviations and where they would come from. When we say an ideal gas, the reason we can call something ideal is it's going to follow those kinetic molecular motions. That they're not, the gases are so small that they're not going to interfere with each other when they're doing their job as keeping this room filled up. When they're keeping the balloon filled. They're not going to hit each other and stick to each other. Because if they did, then all of a sudden the number of moles of gas would be cut in half. If you had 10 particles and they hit and made 5 particles, like they connected together, you just cut your number of moles of gas in half and the pressure is going to be cut in half. That doesn't happen. So under what conditions could we do? Think about a gas particle. Think about this being the balloon and there's gas particles in here. See if you can come up with some reasons where interactions, and that's all you really need to think about, would have an effect on its ability to make the balloon as big as it needs to be. So think of something right now. Can you think of anything? the distance between the molecules. Very good. So right now, you remember, if you're only this big and this big, tiny, and you're in this room, chances are you're never going to hit each other, are you? Because if you do hit each other, there is a probability you could get an interaction. So you don't want to hit each other. You don't want that to happen. So you want it to be so far apart that chances are they're never going to hit each other. So, yes, Seth, what can I do?
Well, polarity is a little like it negative, they're both negatives, like
They do repel each other. Okay, well, the gases are generally non-charged, but they could be polar. That is a possibility. They could be polar, and even then, they might even be somewhat attracted. Now, that brings up a good one.
Yeah.
Even polar molecules, they can be attracted to one another. And if they're attracted to one another, not only do they not even have to hit, but if they get into close proximity, they might pull toward each other. That's bad. Then you have two particles that are acting like one. And that's going to be a heavy molecule. It's going to start moving slower. You're not going to get the same pressure on the wall. So you're going to have this big fluctuation. It's almost like you're watching a balloon go. That would just be kind of weird, sitting there watching a balloon do that. Because you're getting all these interactions. You've probably seen that when you're high sometimes, but not normal life. So it's going on like this, right? Now, the thing is so again, let's think. So what are some things that we could do, physically do, that would cause some of these interactions to occur? And I think you kind of alluded to it, sort of, what you were saying. But tell me, so what could we do physically to make that happen?
Make collisions happen?
No, because right now the reason why they don't interact, like you said, is the distance between the particles and each other are so vast. It's like they never see each other. So how can we make it see each other? Okay, he said compress the gas. What were you going to say, sir?
Decrease the amount of space there.
Decrease the amount of space, which is the same thing as compressing the gas. Very good. What if you took the volume down so small that now the area is this big and the particles are this big? You know what I mean? Like they're this big. I mean, they're going to hit a lot. So you got one of them right then. So by doing that, by decreasing the volume and keeping the same amount of moles of gas in there, you have exponentially increased the pressure. So if you increase the pressure of the gas by decreasing the volume, you're going to get non-ideal behavior. Non-ideal behavior becomes where you're going to have molecules interacting. You don't want that. So high pressure is a non-ideal situation. So what's another way we can do get the same effect? Yeah. Okay, actually, low temperature. Low temperature, think about what happens in low temperature. Low temperature, the molecules slow down, and if you imagine, if you take a balloon this big, you put it in the freezer, then look at it later, it's this big. What'd you do? You decrease the volume again. You didn't change the number of moles, so again, by getting the molecules closer together, there's that high probability that they could interact. So there you've got it. It's just those two things only. It's high pressure, bad. Low temperature, bad. All of a sudden, those gases will not behave ideal anymore. You'll get interactions, and you don't want interaction. High temperature, the gas is going to expand and get even further apart, so they're probably never going to drop. So high pressure is good. High temperature is good. Low pressure, very good. The lower the pressure, the further the molecules are apart as well. Okay, so. No, decreasing the temperature, not on the same gas. If you did, that's assuming that the walls of the container can move. Yes, I see what you're saying, but no. But at low temperatures of a gas, the gas molecules get closer together, and then there's more chances of them interacting. And you got to get really cold. You almost got to get to a point where the gas is going to liquefy. Then it's going to get to a point where it's really going to deviate. So if you look at this next couple of slides, and these are just this is deviation from ideal behavior. If you notice, if we start increasing the pressure a lot, notice you start getting deviations, positive or negative. This is for pressure only. Obviously, the more under the higher pressure, you're going to get gas molecules closer together. They don't want to be close together. And the other one is, what is this one? Assumption. Oh, this is just showing you what I just talked about. This is pressure, same thing. And it's just a bunch of stuff. Now that you know that high pressures and low temperatures, those are the two things that cause molecules to be too close together, deviations occur, you can't use the ideal gas equation anymore. you'd have to use this one, the van der Waals equation. This one takes into account those two things we talked about. The pressure term, which is, here's the pressure term in the bracket, you got to take in basically the number of moles per volume that it's actually occupying. So there's going to be the pressure you got to take into account the molecules themselves. And you never take into account the size of the molecule itself using an ideal gas equation. You don't need to, because they're so far apart. You don't even measure their volume. The volume term, you got to do the same thing. You got to take into account minus, you got to subtract out the actual volume of a gas particle. You got to subtract it out, because it actually is contributing now to the overall volume, because things are so close together. And again, the first term, when I said you add, since it's pressure plus, you actually got to add a force that of attraction or repulsion that's taking place between the molecules because they're so close together. So, in other words, if the pressure exerting outward was some number by themselves, when they get close together, these two guys might attract each other. That's going to reduce the pressure that is pushing on the Waals container. Are you with me? If they're this far out, it's pushing, great, a lot of pressure. If you get them too close together, that outward push might be affected by an inward pull on the two molecules. So that's going to reduce your pressure some. So you got to add that into account as well. I'm not going to make you calculate anything with this. I just want you to see the equation. On OWL, if you have to, fantastic. I'm not going to make you use the van der Waals equation to calculate anything on the ground. I just want you to see it. Is that clear? Yes. Yeah. That's everything. All right. So our test is on chapter 4, 5, and 6. What's 4 about, Seth? Don't look. You just got to know. What's 5 about, Johnny Cash? It's stoichiometry in solution is 4. And 5 was what? Everybody was 5. Thermochemistry. And then 6 was the gas law. So we got 3 very diverse chapters. But all of them have a common theme. They're all going to use stoichiometry. All of them. All of them have units you're going to deal with. All of them are going to, even though they're 3 very separate units, solution stoichiometry, heat stoichiometry, gas stoichiometry. So that's kind of what we're looking at. Are there any questions about anything before I maybe start a review session with you? Okay, you want to, here's an exam I used last year. We'll kind of look at it. I'm not going to do all of it, but I might pick a couple of good questions so you can kind of see how it works. Go to the help session, the SI, and he's going to help you with the report. But I don't know. Tell me, I don't know, even know what you guys are probably going to struggle with the most. So if you kind of give me an idea of those 3 chapters, what particular area of those 3 chapters are you kind of concerned about, and I might be able to help you. Yes, ma'am.
You can put this on OWL or,
I wasn't planning on it. He can.
I'm going to email the practice test out.
He's going to email the practice test the day after the test. He's got to email it to him today.
2 days after?
Yes, ma'am. Oh, wait, I know your name. Lexi.
the solubility rules, you have to know those, or going to get those to us?
The solubility rules, let me see. I think there's one on here. See, like in this one, you have to know them, and I don't believe I gave the solubility rules. I think I wanted you to practice them enough. If you do enough OWL questions, you should be able to answer. Look, let's try to do this with lexicon. Let's do this. Which compound listed below is soluble in water? Which compound listed below is soluble in water? I'm asking Lexi. Hey, Lexi, is lead chloride soluble in water? See, you should know this one. Because chlorides are soluble except for silver, lead, mercury. So that one's not soluble. What about silver? Now this one's easy, Lexi. Silver nitrate soluble, yes or no? How do you know, Lexi?
Because nitrates are solid.
Very good. All nitrates are soluble. That's very good. Hydroxides are not soluble, except for the group 1A and some of the 2As, like barium hydroxide, and so that one's definitely not soluble. And carbon bases are not soluble, except for the group 1A and a few other ones. So there's not many of the rules, so I would kind of go over them. That's something.
But it's gonna be questions like that or questions kind of like how, I don't know if you know.
Well, look at the
how
next
are.
Which equation is the net ion equation for the reaction of PbNO3 and Si? So here you need to know that Pb and PbI is not soluble. So that's going to be the one with the solid. So there's, and that's kind of an easy question because there's only one of them that, no, this one has PbI too as well. But, yeah, but cesium nitrate soluble, so that would not be in that equation. So, yeah, I'm trying to think. The solubility rules? Yeah. Yes, sir. Now, acids and bases, you better know. You need to know the 6 strong acids, and you need to know the strong bases. Those for sure. I'm not giving you those. No. So you I'll think about that. Yeah, both of those are easy, right? I mean, so they're not going to get any harder than that. I mean, if I give you the rules, I might make the questions harder. If I don't give you the rules, I'll make them simple like that. Yeah, that's what I thought. Yes. Yes, sir. He said, is there a reason why silver, mercury, and lead, fluorides, iodides are not soluble? Is there the actual kinetic, or not kinetic, that would be physical reason? It's got everything to do with laws of attraction. It's got everything to do with a water molecule. It's just like, why is oil not soluble in water? In order to have it, the attraction between a lead iodide and another lead iodide is so strong that it doesn't want to break apart, and you don't get any energy back when a lead iodide and a water molecule attract each other around them. So there's not a net gain in thermochemistry and enthalpy and entropy. So it's just, that's why. But next question. Help me, Daniel. What do you want to know, son? Yes, Chris. Yes. She's asking now. You're like that. Go ahead. All acids and bases are soluble. Yeah. All the strong acids, strong, and completely dissociate 100%. Yeah. Next question. Yeah. Yeah, let's look and see how I might do a calorimetry problem. See, those are good questions. Thank you. Calorimetry problem, let's see. I know there's got some on here. Yeah, here's one. Look at this one. This is a good question. It says, can you guys see this back? Now you can. When 50-gram sample of metal at 100 degrees Celsius is added to 60 grams of water at 25.1 degrees Celsius, the final temperature of both the water and the metal is this. Wow. We did an example exactly like this in class. So, not this one, but exactly. What is the specific heat of the metal? So that would be a way I would ask it. I mean, that's one possible way. There's not that many ways to ask it, as long as you know the equation. Now, what is the equation for heat capacity? Delta T Q equals C delta T or CS delta T, specific heat times change temperature. So if you know that equation, that'd be an easy one to do. Okay? I mean, do you need me to do this question, or yes or no? Yes. Okay, let's do this. Unfortunately, I'm going to have to do it while you guys look at. While I'm doing this one, why don't you look at the one underneath it and see if that one's giving you any issues? Because I got to be able to see it in order to do it. So give me a second. about what's about to happen. When I take that 50-gram piece of metal and I drop it into a glass of water that has 60 grams of water, which one's hottest, the water or the metal? The metal. The metal is at 100 degrees Celsius. The water is at 25.1 degrees Celsius. So when I drop it in, think in terms of Q. Where is Q going? Into the water from the metal. So Q is going to leave the metal. Now, the amount of Q that the metal loses is exactly equal to the amount of Q that the water gains. Do you agree? And at some point, they're going to get to exactly the same temperature when Q quits going back and forth, or going in one direction only, from hot to cold. So it's going to. So with that information and the equation Q equals mcs delta T, it's easy. Here's how you solve this. So it's coming. Nope. Okay. Okay, so basically, let's look at what I wrote. Don't worry about the minus sign you get, but Q of the metal. Q of the metal is equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. Now, is equal to the change in temperature of the water times the I got these out of order, but the mass of the water times the specific heat of the water times the change in temperature of the water. Now the reason why I put the minus sign, because really we know that minus Q of the metal is equal to Q of the water. Because the metal is going to lose Q. The water is going to gain Q. It's going to be exactly the same amount. So if I take minus Q of the metal, so that's where this minus sign comes from, and it'll make sense to you when you do it. Because what is this number? This is the change in temperature of the metal. 32.8 minus 100. Final minus initial. Guess what that's going to be? A negative number. So the negative sign is going to turn that negative to a positive, because you can't have a negative answer. So there's the mass of the metal, the specific heat of the metal we want to calculate. There's the change in temperature of the metal. There is the change in temperature of the water times the mass of the water times the specific heat of the water, which was given. Then just solve for x. X equals 0.576 joules per gram degrees Celsius. So I mean, that's how you do it. So pretty straightforward. Got it?
Yeah.
I'll keep it up. Saw a pretty good movie last night. Live, die, repeat. Live, die, and repeat.
As you tomorrow.
Huh? No, it's actually called Live, Die, and Repeat.
It was.
Oh, yeah. Oh, what's the name of the movie? Oh, I read it on YouTube.
Hun, you're the best. I was like watching it go. Like, it's gonna go a while. Thanks, Casey.
Yes.
You're right. It's actually called Live Die Tomorrow. They changed the name.
It actually is called Live, Die, and Repeat.
It was Edge of Tomorrow, and it was Live Die Repeat. It was Edge of Tomorrow, but they changed it because it didn't get.
Oh, they
many views.
changed it to Live, Die, Repeat.
Yeah.
Are we done?
They changed it. They changed it like 3 times. First it was just like, what is it?
What time?
Tomorrow, and they changed it to like Edge, and then Live Die Repeat.
Hey, why don't we do this? Let's stop for a second. Some of you might not need all this exercise, but I'm going to give everybody a chance. It's not going to cost you anything, because we've got about 30 more minutes, and I don't mind sticking around, answer some questions, but he's going to email these to you, and and you can try to work them out. If you have any questions, definitely go to the SI. But if any of you want to just get on out of here, I promise it's not going to hurt my business. But go ahead and go, but I'm giving you this opportunity now to go. Anybody on the stage, you're going to stick around. It doesn't fit. You can get up and go. So go.